Swayam Prabha. Digital India. Educated India.
Welcome to lecture 11 on time series modeling and forecasting. Now, in this lecture, I will discuss some stationary processes for time series modeling purposes. First, I will start with the Wold decomposition, and then I will discuss some general I will discuss the general linear process. Wold decomposition or Wold representation theorem states that a zero mean covariance stationary non-deterministic process can be decomposed as yt equal to I equal to 0 to infinity theta I ut minus I plus mu t. Well, I am not going to give you the proof of this result. Now, here for I equal to 0, theta naught is equal to 1. We also assume that summation I equal to 0 to infinity mod theta I square is finite. Then ut is a purely random process and it has mean 0 and constant variance. Mu t is a purely deterministic process. In the last lecture, we have already discussed and I defined the deterministic process. Theta i's and ut's are unique. Expectation of mu t us is equal to 0 for all t and s. So, under these assumptions, you can write any zero mean covariance stationary non-deterministic process in this form, and this representation is called the Wold representation. Then a zero mean non-deterministic covariance stationary process yt is called purely non-deterministic if the purely deterministic component mu t is equal to 0. So, if mu t is equal to 0, then we call this process as a purely non-deterministic process. Now, some of the important aspects of Wold decomposition are as follows. Now, it allows the dynamic evolution of yt to be approximated by a linear model. So, it represents yt as a linear function of ut's and past values of ut's. So, you can say the process has evolved, or at least approximately it has been evolved by a linear model, and this linear model is the only possible representation relating the observed values of yt to the past evolution of purely random process ut minus 1, so on. Remember, these theta i's and ut's are unique. So, this representation is unique representation. Of course, this representation depends on an infinite number of parameters, but in practice these parameters decay rapidly. Another form of Wold representation is as ratio of two finite lag polynomials. Again, I am not discussing here the proof of this result. Under general conditions, the infinite lag polynomial of Wold decomposition can be approximated by the ratio of two finite lag polynomials. Say psi b is equal to theta b upon phi b, where phi b is equal to 1 minus phi 1 b minus phi 2 b square and so on minus phi p b to the power p. Theta b is equal to 1 plus theta 1 b plus theta 2 b square plus so on plus theta q b to the power q. So, what is the difference between these two representations? The first representation, this representation has infinite number of parameters, and then you have further approximated this representation by the ratio of two polynomials, and both the polynomials have finite lag. So, now the number of parameters is finite. Actually, psi b has p plus q parameters. P parameters phi 1, phi 2, phi p, and q parameters theta 1, theta 2, so on theta q. Actually, this second representation forms the basis of ARMA processes, which we will discuss in later on. Now, we consider general linear process. The following process is called the general linear process. Y t equal to mu plus u t plus summation I equal to 1 to infinity theta I u t minus I. So, actually this general linear process also evolves from the Wold decomposition. Here again u t is a purely random process, and u t has mean 0 and variance sigma square u. You can easily verify that the mean of the process is mu, expectation of y t is mu. Now, suppose you take mean mu equal to 0, then you can write the general linear process as y t equal to 1 plus summation I equal to 1 to infinity theta I b to the power I u t. And then we write theta b equal to 1 plus summation I equal to 1 to infinity theta I b to the power I, or you can also write it as summation I equal to 0 to infinity theta I b to the power I, where theta naught is equal to 1. Then you can write this general linear process 3 as y t equal to theta b u t. So, in fact, what is the role of theta b? Suppose you consider u t and y t as two time series. U t is a time series and y t is a time series. In fact, u t is a purely random process. Then y t is equal to theta b u t. So, in fact, this theta b connects u t with y t, or you can say that theta b transfers the changes in time series u t to time series y t. Whatever changes occur in u t, those changes are transferred to y t through theta b. So, theta b is also called the transfer function. Transfer function because it transfers the changes in u t's to the time series y t. So, here the transfer function theta b is an infinite degree polynomial in B, summation I equal to 0 to infinity theta I b to the power I. Theta b is also called an impulse response function. The input u t consists of a unit impulse at time 0 means suppose u naught is equal to 1 and u t is equal to 0 for all t not equal to 0. Then the output is say y t is equal to theta naught u t plus theta 1 u t minus 1 plus you get a term here theta t u 0 plus theta t plus 1 u minus 1 plus so on. Now, u t has a unit impulse at time 0 means u naught is equal to 1, all other u t's are 0. So, if in this relation we take u naught equal to 1 and all other u t's as 0, then what you get? You get y t equal to theta t. So, these theta weights give the response when the input is an impulse. Actually, in signal processing, discrete time unit impulse function is defined as delta n equal to 1 if n is equal to 0 and delta n is equal to 0 for n not equal to 0. Another term which is used for theta b is linear filter. Actually, theta b models the interrelationship between input white noise process or input purely random process u t and the output time series y t. Now, how we define a filter? A filter is an operator given a time series u t, it maps to a time series y t. So, you have an input time series u t, then you are using theta b and through theta b you get the time series y t, or you can say it maps to a time series y t. So, that is why theta b is called a linear filter, and you can say that y t is a linear filtered version of white noise process. So, in fact, you started from a white noise process, a purely random process u t, and then through this linear filter theta b, the time series ut maps to a time series yt. Here theta b equal to 1 plus summation j equal to 1 to infinity theta j b to the power j is the linear filter, and this linear filter is time invariant or shift invariant. It does not depend upon t, or with the shifting of time it does not change. It is not like that at time t you have one filter, at time t plus 1 you have different filter, linear filter. It is time invariant or shift invariant. Theta j's are called the filter coefficients of the linear filter. So, basically the purpose of linear filter, particularly in the context of signal processing, is that it starts with the time series. Through linear filter we get the signal, and the remaining portion is the noise. So, it detects signal from a mixture of signal and noise. Anyway, under certain conditions you can write the general linear process as a weighted sum of past values of yt's plus ut. Means in Wold decomposition, what you have done? You are writing yt as a function of, or as a linear function of present and past shocks. In this form of general linear process given in equation 5, you are writing yt equal to summation I equal to 1 to infinity phi I yt minus I plus ut. So, now it is a function of past values of yt's. Actually, it is a weighted sum of past values of yt's, and then you have this ut, which is termed as shock. So, suppose you write phi b equal to 1 minus summation j equal to 1 to infinity phi j b to the power j. So, you take all these terms towards left hand side. So, what you get? Yt minus phi 1, you can write yt minus 1 as pyt minus phi 2 b square yt minus 1 equal to ut. And then you can write this term as 1 minus phi 1 b minus phi 2 b square minus 1 y t equal to ut. Then suppose we write capital phi b equal to 1 minus phi 1 b minus phi 2 b square so on. Then you can write the process 5 as capital phi b y t equal to u t in this form. Of course, in some other lecture we will discuss the conditions under which we can express the general linear process in this form. But just for illustration purpose, how you can write the first form of general linear process into the second form, let us consider this process y t equal to u t plus theta 1 u t minus 1, or you can also write it as 1 plus theta 1 b u t. Then you can express u t's in terms of y t. So, from this equation u t is equal to y t minus theta 1 u t minus 1. Then you can write u t minus 1 equal to y t minus 1 minus theta 1 u t minus 2. So, what you get? Y t minus theta 1 y t minus 1 minus theta 1 square u t minus 2. And then we proceed further. At last you get y t minus theta 1 y t minus 1 minus theta 1 square y t minus 2 plus so on. But then you have to impose one condition, mod of theta 1 is less than 1. Means otherwise the value of this term keeps on increasing as you proceed further. So, we impose the condition that mod of theta 1 is less than 1, or you can write it as 1 minus theta 1 b minus theta 1 b square minus 1 y t is equal to u t. So, in this case phi j is equal to minus theta 1 to the power j. Now, we consider equation 6, which is phi b y t is equal to u t. Now, suppose you apply the operator theta b on both sides of 6. Then what you get? Theta b phi b y t equal to theta b u t. Then theta b u t is equal to y t. So, theta b phi b y t is equal to y t. So, from here you can write theta b phi b equivalent to 1, or phi b is equivalent to theta b inverse, or theta b is equivalent to phi b inverse, or you can write this relationship in this form also, 1 minus summation j equal to 1 to infinity phi j b to the power j equal to 1 plus summation I equal to 1 to infinity theta I b to the power I whole inverse. Now, this relationship 7 can be used to derive the phi weights in terms of theta weights. It can also be used to derive theta weights from phi weights. Now, we obtain the auto-covariance function gamma k of a general linear process. Now, a general linear process with mu equal to 0 is y t equal to u t plus summation I equal to 1 to infinity theta I u t minus I. then gamma k is equal to, of course, the process has mean 0 because mu is equal to 0. Then gamma k is equal to expectation of y t plus k. Gamma k is equal to expectation of y t plus k. Then we substitute y t equal to summation I equal to 0 to infinity theta I u t minus I, and y t plus k equal to summation j equal to 0 to infinity theta j u t plus k minus j. And remember that we have taken theta naught equal to 1. So, for I equal to 0 you get the first term u t, or you can write this as expectation of summation over I summation over j theta I theta j u t minus I u t plus k minus j. Now, remember u t is a purely random process. So, expectation of u t plus k is a, or better if we take u t plus j equal to sigma square u if j is equal to 0 and it is 0 otherwise. So, here in this double summation only those terms have non-zero expectation which involve a square of u t or u t minus I say. So, we take t minus I equal to t plus k minus j. So, only those terms for which t minus I is equal to t plus k minus j, the expectation is non-zero, and for all other terms the expectation is 0, or you can say for those terms for which I is equal to j minus k, or j is equal to I plus k. So, if j equal to I plus k, then expectation of u t minus, you get a term with the expectation of u t I minus I square, which is equal to sigma square u, and for j not equal to I plus k, you get a term expectation u t minus I u t plus k minus j, which has expectation 0. So, finally, the value of gamma k is, say, summation I equal to 0 to infinity theta I plus k expectation of u t minus I square, and then you get the terms summation I equal to 0 to infinity j not equal to I 0 to infinity theta j expectation u t minus I u t plus k minus j, and all these terms have expectation 0. So, ultimately, and this term has expectation sigma square u. So, ultimately you find gamma k equal to sigma square u summation I equal to 0 to infinity theta I plus k. Then from here you can also obtain the auto correlation function for the general linear process. And then what happens for k equal to 0? You get the variance of the process. So, variance of the process is for k equal to 0, you can easily obtain the variance of the process. Sigma square u summation I equal to 0 to infinity theta I square. So, you have the auto covariance, you have the variance. So, you can easily obtain the auto correlation function. Now, we define the auto covariance generating function. The auto covariance generating function of a general linear process with auto covariance function gamma k is defined as gamma b equal to summation k equal to minus infinity to plus infinity gamma k b to the power k. So, suppose now we prove this result. Suppose f is equal to b inverse and f is the forward shift operator defined as f y t equal to y t plus 1. Then the auto covariance generating function for the general linear process is gamma b equal to sigma square u theta f theta b, or you can also write it as sigma square u theta b inverse theta b. Now, we prove this result. For the general linear process, we have already derived the expression for gamma k. So, we substitute this value of gamma k in the expression for auto covariance generating function, and then we obtain gamma b equal to sigma square u. You have summation k equal to minus infinity to plus infinity. Then we have replaced means gamma b is equal to summation k. You have replaced this gamma k by summation over I theta I plus k, and then you have sigma square u and b to the power k. So, in this expression we have replaced gamma k by this value of gamma k. Then we interchange the summation signs. We take summation from j equal to 0 to infinity first, k equal to minus infinity to plus infinity, theta j plus k, b to the power k. While doing so, we have assumed that theta minus I is equal to 0 for all I equal to 1 to so on, because in this summation you will find many terms involving thetas with the negative index, terms involving theta minus i's. So, we take those terms those theta minus i's to be equal to 0, and then you write it as sigma square u summation j equal to 0 to infinity, and since theta minus I is equal to 0 for I equal to 1 to so on. So, you start from the value of k equal to minus j, because for values of k less than minus j, this term is equal to 0, means for j plus k less than 0, or for k less than minus j. So, we start from k equal to minus j and go up to infinity. Now, we write j plus k is equal to h, or k is equal to h minus j. Then we obtain gamma b is equal to sigma square u, j equal to 0 to infinity, h equal to 0 to infinity, theta j, theta h. We have written h equal to j plus k, then b to the power h minus j, k is equal to h minus j. And then you can write it as sigma square u summation j equal to 0 to infinity. You can take this theta j outside this first summation, and then you can also take b to the power minus j outside this first summation over h. So, you get summation over j theta j b to the power minus j, summation over h theta h b to the power h. Now, this is equal to sigma square u theta b inverse theta b, or you can also write it as sigma square u theta f theta b, where f is the forward shift operator. F is equal to b inverse. So, we observe that for the general linear process, this relationship 3 gives gamma b as a polynomial in B. We just use this relationship. You get gamma b as a polynomial in B. Then using this auto-covariance generating function, you can obtain gamma k, which is the coefficient of b to the power k in gamma b. And once you know gamma k, then you can determine the ACF rho k also. So, what you have to do, just simply multiply theta b by theta b inverse, collect different powers of b, b to the power 0, b to the power 1, etc. Of course, you have to multiply by sigma square u also, and then suppose you have to obtain gamma k, then you just look at the coefficient of b to the power k in this expression, and that gives you gamma k. Now, we obtain the auto-covariance function of the following processes using the auto-covariance generating function, and we assume that variance of the purely random process u t is equal to 1. So, first we consider the process y t is equal to u t plus 0.5 u t minus 1. So, for first example, the theta b is equal to 1 plus 0.5 b. So, your auto-covariance generating function is 1 plus 0.5 b into 1 plus 0.5 b inverse. Now, we multiply these two quantities and then we arrange the terms in the b. So, the first term is 0.5 b inverse plus, then we take the terms involving b to the power 0. So, you get 1.25 b to the power 0 plus 0.5 b. Now, the coefficient of b to the power 0 gives you gamma 0, means this is the variance of the process. Then the coefficient of b to the power 1 or b to the power minus 1 gives you gamma 1. So, gamma 1 is equal to 0.5, and it does not involve any other power of b. So, gamma k is equal to 0 for all k equal to 2, 3, so on. Means for all k greater than or equal to 2, gamma k is equal to 0. Next, we consider the second example. For the second example, theta b is equal to 1 plus 0.3 b minus 0.4 b square. So, you can easily obtain the auto-covariance generating function gamma b equal to 1 plus 0.3 b minus 0.4 b square multiplied by 1 plus 0.3 b inverse minus 0.4 b minus 2. Again, we multiply these two terms and we arrange the product in the powers of b. So, the first term, which involves b to the power minus 2, is minus 0.4 b minus 2, which you get by multiplying this term to 1, and then you have the terms involving b inverse. So, for obtaining the terms involving b inverse, you multiply minus 0.4 b minus 2 with 0.3 b and 0.3 b inverse by 1, and finally, you obtain 0.18 b inverse. Then to obtain the terms having b to the power 0, you multiply this 1 by 1. So, 1 plus this term by this term means 0.3 b by 0.3 b inverse. So, you get 0.09 plus the third term minus 0.4 b square by minus 0.4 b minus 2. So, finally, you obtain and then you have or better if we write this term here. So, from here you obtain gamma 0 equal to 1.25, gamma 1 equal to 0.18 and gamma 2 equal to minus 0.4, and gamma k is equal to 0 for all k greater than or equal to 3, means from k equal to 3 to for k equal to 3, 4 and so on, gamma k is 0. Next we consider the third example. In the third example, on right hand side you have a polynomial of infinite degree in B, and the terms are decreasing exponentially. Anyway, you take theta B, theta B inverse, and multiply these two, and then you will get the autocovariance generating function. So, this is equal to 1 plus 0.5 B plus 0.5 square B square plus so on into 1 plus 0.5 B inverse plus 0.5 square B minus 2 plus so on. Again you multiply these two terms and arrange the multiplication in the powers of B, and then you can easily check the coefficient of B to the power 0 is gamma 0 equal to 1 plus 0.5 plus 0.5 square plus 1. You have an infinite geometric series, and the value of this series is 4 by 3. Similarly, the coefficient of B to the power 1 will give you gamma 1, which is equal to, say you multiply this term 0.5 B by 1, 0.5 square B square by 0.5 B inverse, and finally you obtain again you obtain the geometric series, and the sum of this geometric series is 0.5 into 4 by 3. Similarly, the coefficient of B square will give you gamma 2, and then you can easily verify that this is equal to this is 0.5 square into 4 by 3. In general, you can easily check that the coefficient of B to the power k, which gives you gamma k, is equal to 0.5 to the power k into 4 by 3. So, this is how you can obtain the auto-covariance function for this process using the auto-covariance generating function. So, this is one procedure for obtaining the auto-covariance generating function. You can obtain all these auto-covariance generating functions directly also. So, in this lecture we have considered the Wold representation for the time series, and Then we have considered the general linear process also. In general linear process, we represent yt by the current shock as well as by the past shocks. It is a linear function of current shocks and the past shocks. So, it gives you an idea of how the current observation yt is generated or it has been evolved by the past shocks. We have also discussed how we can obtain the auto-covariance function using the auto-covariance generating function. From the next lecture, we will move to different stationary models which can be used for modeling a time series. Those models include the autoregressive model, moving average model, mixed dharma models, etc. So, thank you.
Hello and welcome to this piece of literary snippet. Perhaps the most popular literary genre after novel is the short story. Sharp, compact narratives whose charm lies not only in what is said, but also in what remains unsaid. Today I will be reading one of the shortest instances of a short story that I have ever encountered, and indeed the very charm of this particular story that I am going to read out today lies in the way it abruptly ends. It is an ancient tale from Mesopotamia which has been retold by several authors, among whom the name of Somerset Maugham stands out. The adaptation that I will be reading out is perhaps the closest to the one that Maugham wrote. The story is titled in all of its adaptations almost as Appointment in Samara. Here is the story. A merchant in Baghdad once sent one of his servants to the market. The servant was supposed to buy provisions for the merchant, but when he returned, he came back empty-handed. Indeed, the servant had all gone white, and trembling with fear, he told his master that he had met death in the marketplace. When I entered the market, the servant said to his master, I was jostled by a woman, and when I turned to look at her, I saw that she was death. I am very scared, master, because death looked at me with a threatening gesture. Can you please lend me your horse so that I can fly away from Baghdad to the town of Samara and thereby escape death? The master, being a good man, gave his servant his best horse and saw him gallop off to Samara to escape death. Then the master himself went to the marketplace and confronted death. Why did you make a threatening gesture to my servant? Asked the master to death. And death replied, it was not a threatening gesture. Rather, it was a start of surprise. I was astonished to see your servant here today, because this evening I have an appointment with him in Samara. See you in the next episode of Literary Snippet.